All right, hello. In this screencast, I want to take a look at the Chapter 4 problem set. And so I asked you to complete exercise 4.4. So we're continuing to build upon our friction factor code. And so I'm going to start with what I had created for the screencast for Chapter 3. And so basically, we're asked to take a series of steps in which we're going to update our code based on some of the tools we learned in Chapter 4 in terms of working with scripts. So in the first iteration, we're going to update our script so that each loop iteration, the computed friction factor is stored to a vector. Then for 2, we're also going to create a vector of Reynolds number, and then we'll loop over the elements of that Reynolds number vector and compute the friction factor for each case. And then finally, in the last case, we will replace the for loop altogether and just use element-wise operations. And so I'm going to flip over to MATLAB, and this is the script, the version of the script that was posted for Chapter 3, right, and along with the Chapter 3 screencast. So I'm going to start with this and have some fun updating it. Okay. So I'm going to go over to my editor. Let me see if I can open this in full screen, and let's take a look. Okay, so we didn't have any preconditions, but it's going to plot friction factor versus Reynolds. And then we had it separated into 2 cases. All right, and so if I just look at 2 cases, or look at case 1, so we defined the relative roughness for case 1, opened up that figure window, we had our constants lambda 1 and lambda 2, or lambda 1 and tau 1, computed lambda 2 and tau 2, which are just dependent on that relative roughness. Then we looped over our Reynolds number. Okay, so all right, so this very first version, okay, I'm going to call this, so this is case 1. So this we want to, instead of having the scalar at the friction factor, we want to store the results to a vector. Okay, and so what I'm going to do is I like to use capital letters for vectors. So instead of little f, I'm going to call that big F. I'm going to call it F1, right? So it's F1 because it's case 1, so I can keep track of things. And then what I'm going to do is now this is a little tricky, right? It's a little tricky in that my loop, right, is I'm actually looping over Reynolds numbers. And so this is going to go from 1 times 10 to the 3 to 1.1 times 10 to the 3 in increments of 1. And so I'm going to actually have to create my own kind of counter variable. So I'm going to call it a loop index variable. And so I'm going to start by initializing I with the value of 1. And then the start of each iteration, I is going to be equal to I plus 1. All right, just so that I can write to the ith element of F1. Okay, so the first loop iteration, I is going to be assigned a value of the current value of I plus 1, so that 0 plus 1 is 1, right? Remember, my loop indices start at 1. Okay, and this is just an exercise. Ultimately, we will improve it. But if I want to create a vector of values, right, I'm going to create this vector F1, and then I is just going to keep track of the index I'm currently writing to. So 1, then 2, then 3, then so on and so forth, only because my loop index variable here is Reynolds, and it doesn't correspond to an index. I mean, I could use it, but then what would happen is I'd create a vector where the first 999 entries are zeros, right? Because it's going to start writing at the 1000th element. Okay. So cool, right? And so we had commented out the figure because figure is active, and then this would just get updated so that I plot the ith element since we're doing it in this way. Okay. All right, now F1 it's going to complain a little bit about, right? Why it's complaining about F1 is I'm defining it dynamically. We'll be able to resolve this issue once we create a vector of Reynolds for part 2. So for now, I'm just going to leave it. Right? It's okay to define your variables dynamically. The issue is just remember for a scalar, so if I have a 1 by 1 vector, MATLAB assigns 8 bytes of data to store that information. So when I have a vector, when I have multiple numbers, right, in this array, MATLAB's going to assign 8 bytes of data per element of that vector. And so what it's complaining is, as I'm defining my vector graphic or dynamically, so each iteration I'm adding an element to that vector. So each iteration it needs to allocate another 8 bytes of memory to that variable, and that's what it's complaining about. But all right, so I'm going to do the same thing down here. Okay, and this is just for so I need to reinitialize I. Bam. And then I'm going to call this F2. And then I'll plot F2I. Okay, so then hopefully if I run this, okay, remember my face is in the way, which makes it a little harder in terms of moving out of full screen, but that's okay. The desired result is just plotting, so I'm going to click the run button. Right, it's this blocks my, re-minimizing my editor. But anyways, so I get my two plots of friction factors. They look just like before. Okay, and what I'm going to do is I'm going to save this as friction factor plot 1. All right, so I can post it as the update for each part. Okay. All right, so now I'm going to save another copy of this, and I'm going to call this friction factor 2, just so I plot it, where I take into account the second part of the problem. So in the second part of the problem, right, I have I'm using Reynolds as my loop index variable. And so what we want to do here, what we often do instead is we have, say, a vector of Reynolds values, and then we just loop over the elements of that vector. Okay. And what I mean by that is what I'm going to do instead is I'm going to create my vector of Reynolds numbers. Okay. And I probably would actually do that up here. That way if I want to edit it, I can. Okay. Since the vector of Reynolds number is the same for both cases, I'd probably actually create it up here. And again, I like to use capital letters to remind myself that it's vector. And so I could, just do this, right? So I could create a vector that goes from 1e to the 3 to 1.1e to the 3 in increments of 1. And that's fine. Okay. But typically, right, and so I'm just going to comment that out so you could have it there if you wanted. What I typically prefer to use is this function linspace. So with linspace, I can just create a vector that goes from some desired lower bound, 1e to the 3, to some desired upper bound, 1.1e to the 3. And then if I just leave it at that, it'll just create a vector that goes from 1e to the 3 to 1.1e to the 3 and 100 of length 100. So it's going to have 99 equally spaced, or 100 equally spaced points. Or you could give it a third argument where you could specify the number of points, right? Say 1,000. Okay. But rather than being constrained by increments of 1, right, you could instead constrain how many points you'd actually like to use. And so then what typically happens is once I do this, right, so now I've got a vector of Reynolds numbers, of how that changes things, okay, is, well, so now when I loop, I'm going to delete the occurrences of I in here. Okay. So typically what I would do now is I would use a loop index variable I, and so I would go from I equals 1, right? So I'm going to loop over my vector of Reynolds numbers. First element in my Reynolds number vector is 1. So I'm going to go from 1, the first element, to the last element. And how I get the last element is I use this length command, right? So length Reynolds, length Reynolds will return the number of elements in Reynolds, right? Or essentially what n is. Right? So if I want to loop over the entire range of Reynolds values, right, I want to loop from 1 to length Reynolds. And, it is, another possibility is I could have a precondition of, say, n, the number of data points, and you could put n in here, all right, and you could loop from 1 to n. But in general, like length, because it's more generalized, you're generalizing your code, your script. So anyway, so I'm going to loop for I equals 1 to length. Okay, I just specified 1,000 here. You could have a precondition and number of data points, but I'm just going to have it all in the script, so I'm not going back and forth. Okay. So now, again, now I can loop over the elements of my Reynolds vector. So then I can actually, do this as I am here, right? So now right, it's just that loop index, so that's good. Okay, but I'm going to have an issue here, and that I've got Reynolds, but I have big RE there. So I could do this a number of ways. Okay, option one would be each iteration I could just assign to RE, REI. Okay, that's probably the easiest thing. The other thing I could do is I could find my occurrences of RE, and I could replace those with just REI. Okay, all is the same. It's a matter of what makes the most sense to you. So this would be one option. The other option would be, I'm just going to copy and paste this because that's what I do, is I just find my occurrences of RE and I just replace them with REI. Okay. So that's my other option. Okay, and if I do that, then this line I can kill too. Okay. Now my plot command, yes, right, I could change this to REI. All right, but what is actually better is now if I take this, I can take it out of my for loop, because now I can plot my vector of Reynolds versus my vector of friction factors. I could plot it all at once. Okay, remember every time I call plot, right, I'm plotting, a set of data. So now when I plot all of my data, right, I'm just plotting a single set of data. And so this also allows me that if I didn't want to, use symbols, I could actually, if I put a dash in there, I could plot it as a line. I could plot a black line. Because before I was plotting my, each point was a set of data, and so it was a, plotted as a tiny little point that I couldn't see. But now that I have a single set, right, I could connect all those points I can actually see. I can actually connect them by a line because I can connect all the points in a set. So that makes it a little clearer. Now the other thing we can do here to clean this up is, again, what it's complaining about here, is we're defining our vector dynamically. And what would be, much better practice is if I know the final size, just to tell MATLAB at the very beginning how big it's going to be, so it can assign all the memory that it's going to need to store, all of the elements that will ultimately be there. And so how we can do that is, let me come up here, and I will create a vector for friction factors. Okay, and so for that I would typically use the 0 command. So I would have a command like f1 is equal to zeros. Okay, now zeros, first argument is the number of rows followed by the number of columns, RC. So one way I could do this is I could do 1 comma, I can do that same length command, right? Because I know I want this to be the same size. It's trying to auto format. I want it to be the same size as my Reynolds number vector. Okay, so that's one option, right? That's how I would typically do it. Right, it's going to be one row and it's going to have that many columns. The other way you could do it is there is also a size command, which you could do zeros, and you can just say I want it to be the same size as Reynolds. Okay, this is also acceptable. Size would return a vector corresponding to the number of rows and number of columns. Okay, so these two would be equivalent. Okay, I'm just going to comment that one out, so that if you wanted to see that, right, you could see it. Okay, or if you want to try it out. Okay, so now that I've created this will create a vector of f1 vector of f1, which is the size that it'll be at the end of our calculation, right, our final size. But initially it's just going to have all zeros. And then you look, when I do that, right, this is no longer highlighted, right, MATLAB is now happy. Cool. All right, so let's do the same thing down here. Okay, and actually I'm going to delete this since those are just constants, and again we don't need it. Now in terms of my Reynolds, okay, I put the Reynolds up here because you only need to define it once. As long as we're going to look at the same range of Reynolds values, I only need to change that once. So I'm going to just delete my index variables. Okay, and then here I'm going to loop for I is equal to, and I guess I could just copy it from above, 1 colon length Reynolds. Okay, that's great. F2I. Then what we did here is these were all changed with REI. And so I'm going to copy it so I can get the others. So that should be all of my Reynolds. Bam. And then the plot command, right? So we can delete this. That was just a comment. And then I'm going to remove this from my for loop. And instead put it down here. But now I can plot all of my Reynolds versus all of my F's. And now I'm going to use a line. Okay. And then I need to presize my F2 vector. And, creating this vector of zeros is also beneficial as well, because if a vector of F2 values existed before, essentially I'm deleting it and I'm creating a new one. So it prevents any issues when we run, our code consecutively if anything were to change. So I'm going to do zeros, and I'm just going to do 1 comma length RE. All right. I could also have created a, variable that was just the length of RE, because now I'm using it in these 2 zeros. And then it also comes in my for loop, but that's just a matter of preference. Okay. So if I run this, okay, now I have 2 plots, all right, but I have lines. Okay, life is good. Okay, so that's part 2. All right, and again, my last comment was, length Reynolds, right? It comes here, 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 right, and here. And so what I even could have done is, after I defined Reynolds, I could create a variable n, which is, say, equal to length Reynolds. And then I could have just put that here, 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 and here, right? It would have all been the same. All right, so far so good. Okay, now in the last version of the code here, it says, all right, what would be really great is if you could just get rid of this for loop altogether, right? And we could do that. And so what I can do now is, now I have a vector of Reynolds numbers, and so I can update this to use element-wise operations, so that it performs the calculation for each element of my Reynolds, and I get a friction factor for each of those cases. And the only part that I need to update with element-wise operations is this part, right? Because this material up here is independent of Reynolds. Okay, and so what this would look like is, I start by delete my for loop. Okay, I'm going to delete this referencing an element I, because I want to do this for all elements of my vector. Okay. And then the easiest, safest thing to do will be, since I'm only thinking in terms of element-wise operations, I'm not thinking in terms of linear algebra at all, would just to go to line 38 and replace all my cases of multiplication, division, and exponentiation with element-wise operations. Okay. And it, that especially becomes true once I have these parentheses and I start to lose track about how these things propagate, right? Because this is going to be a vector, right? My exponential operates element-wise. 1 plus that would be a vector, and so I would need to vectorize this as well, because it's a constant divided by a vector, right? And so the easiest thing would just be division, multiplication, exponentiation. I'm going to go through and change all of those to be element-wise operations. So division, division. I have a case of division here, and then I'm going to throw it in multiplication. Oh, period comes first, and then division there. Division, division, multiplication. Got it all. Okay, and so this is now becomes computing F for all of our RE values. Okay, And then when I do this, right, what this is telling me, and I've got a warning up here, I don't need to pre-initialize, right? This is, hey, you're creating this vector f1, and then you're just overwriting everything. That seems odd, okay? And so, it's unused, right? Because this is, I'm just doing the same thing, I'm creating it. So I don't actually need to pre-allocate f1, so I can go ahead and delete that now as well. Okay, and look how simple this has become. If I do the same thing down here, okay, I'm going to delete the for loop. Okay, I'm going to delete the parentheses I, since I want to operate on my entire vectors. Bam, and then I'm going to go through division, multiplication, exponentiation. I'm going to change all of those to operate element-wise. Okay, just typing something in there. That, and then this, we were able to delete as well. Okay, so let me see if I've got this right now. So if I run it, I get two figures. All right, bam. I was supposed to save this as version 3, so now I just overwrote version 2. Arg. My apologies. So it looks like I'll have number 1 in version 3. But yeah, there it is. And if you ultimately want to, update this, you could make this also work for vector of ed values. If you vectorize with ed, you would then just need to update these to operate element-wise. So then you can give it a vector of Reynolds or vector of relative roughnesses in theory. But now I've completely eliminated the for loop. All right, and what you should find is that this code is much more efficient. So what I'm going to do is that's the solution. I've got version 3 saved. When I stop the recording, I'll try and do Control Z until I get that version 2 back, and then I'll save that version 2 so that I can post them all. If you have any questions, please let me know.